Recording. Okay, so it's our pleasure today to have Professor Laurent Demenet from MIT to give this week's One World Mind seminar. So Professor Demenet received his PhD from Caltech in 2006 from under the supervision of Emmanuel Candace. Since then, he's held positions at Stanford and MIT, where he currently is at now. He's won multiple awards, including the Sloan Fellowship and an NSF Career Award. So you may have seen his work on things like curvelets or super resolution and computational imaging, but today he'll talk to us about recovery phenomena with symmetric autoencoders. So please go ahead.
Thank you so much, Willie, and thanks for the invitation. It's nice to see all of you, and I see good friends in the Zoom room, so it's good to see all of you. I guess I'm going to continue straight on with the pre-talk chit-chat that we had, because I said our students are interested in machine learning. That's what they want to do. There are good reasons for it, and I think the same is happening for us also in terms of research. Deep learning has changed what many of us do, for good reasons, even though the reasons might not be the same. And it's important to realize that, to understand that. So I guess my presentation here today is not so much going to be necessarily, a result that I want to show you, but, among friends, we can also talk about how will that change, or has that changed computational mathematics, and why and how, and is that the case for you too, and what do you think about that? So please interrupt me at any time. This is more like, chit-chatting around the coffee machine than an actual, talk, if you guys don't mind. So again, don't hesitate to interrupt. I love that. First of all, let me acknowledge my collaborators on whatever I'm going to show you here. The topic of symmetric autoencoders has kept us busy for a few years, and this is the work of Pawan Bharadwaj, who was a postdoc in my group and is now on the tenure track at IIS in Bangalore. Matt Lee was a graduate student in my group, is now a postdoc with Youssef Marzouk and is still at MIT. And Borjan Geshkovski, who's currently a postdoc with me at MIT. And will start a tenure track position in France in a couple of weeks. So good for him. So I want to show you a story of how we jumped on the deep learning, train, like many of you. And we do it in the context of scientific machine learning, because we want to make predictions about systems that involve at the same time physical models and data, but in a different way than solving inverse problems. Now we're going to start to see the role of deep learning. I'm going to try to put this in the context of what some other people do with deep learning in our community here. It's not always like that, but for us here, it's going to be inverse problems, but rethought in the context of deep learning. So there's an element of this which is quantitative. It's not computer vision. We actually want to achieve a degree of accuracy, because we're going to try to determine quantities of physical interest for which we want, an epsilon accuracy, things like that. So the game is not, yes, there's going to be generative AI in what I'm going to talk about, but the game is not just to generate something that impresses a human or is useful to a human, but something that is actually an accurate prediction. So this is scientific machine learning. So that's the goal here. And the picture that you see here in the background is of seismic data and seismic models. So we're going to try to see in the context of wave equation-based inverse problems what this might be. So how and when can we use deep learning, starting from where we were about 10 years ago? The two main areas where by themselves deep learning are helpful are in the context where you have data, and you would have what are called black box predictors that only use data and do not use physical models or equations whatsoever. That would be what is usually called supervised learning. But on the other hand, the other bubble I have here is for simulations, because you can use deep learning trained on simulations to then replicate a black box model. A model in a black box fashion. So you would have a PDE simulator, for instance, and then you would have model reduction. DeepNet provides a way of giving you the answer with training from simulations. In fact, the role of simulations and solving PDEs. It's been completely flipped on its head over the past few years, as you know. We don't necessarily use it for its own sake or for inverse problems, but as training sets now for deep nets. Then starting from where this picture was maybe 10 years ago, there's been a lot of interesting contributions in the research community around the community of mathematics, where some really good ideas have come up that link those two paradigms and help make progress at the intersection of the two, where you both have data and you have a model. And so in particular here, I would say some of the things that have impressed me the most over the past several years are how to regress the PDE, for instance, the work of Nathan Koontz, University of Washington, where you have solutions of PDEs, try to find a PDE that explains that, for instance. This is interesting. Subgrid closure models are another interesting area, which is all the rage right now in atmospheric physics and oceanography, for instance, where you want to close your PDEs with subgrid schemes, and deep nets are a good way to do that, for instance. So it's a long list of those that we've seen over the past several years. The math community has made inroads there. What the question I want to get to today is not so much, show you, there's results I'm going to show you, but the questions really are of the type, can we walk back this idea of universal approximations and deep nets and make them look more like the PDEs that we know, that provide interesting scientific prediction? In other words, not just what's going on in a deep net that produces an accurate prediction like solving a PDE does, but is there a way for us to control a bit better what happens in a deep net so it starts to resemble more a partial differential equation or a model coming from physics? And in particular, I want to show you the idea that you can assign meaning sometimes to some components of a neural network and say that they acquire meaning and they help to disentangle explanations. They help to, if you assign them different roles, they will be responsible for whatever the prediction is. And so this disentangles the explanation. And if you can do that, if you can give meaning to some of the components of neural network, then all of a sudden you can do more than just reproduce a training set or interpolate a training set to get testing, but you can do more general things like read datum, meaning generate unseen data. So if you think about a situation where you have seen solutions of a partial differential equation, but you want to look at a nearby case where you want to tweak parameters in the equation, what would your solution look like, for instance, without ever looking at the PDE, but asking to do this tuning, then this is something that might be possible if you have such a representation of solutions of an equation. So redataming, and I'll show you examples of this. Here's the first example. I'm going to borrow it from computer vision to motivate what I'm going to do later. It's the idea to represent here one of the very simplest databases for machine learning is called the MNIST database of these tiny 30 by 30 images of handwritten digits. So you have a bunch of those, and you'd like to be able to, let's say, classify them. This is a very, very standard task in machine learning. What I want to do here is in fact use this example to talk about the notion of explanatory components in a prediction task. So here, what you'd like to be able to do is say, when you have a data set of handwritten digits, the different types of information, there's a coherent information here that's common to all the images you see on the left, which is the content that we're talking about, the digit 3. And then you have the dissimilarities between these images, which is due to the writing style. It's going to be depending on the user, whoever wrote these digits. So you have extra information here, which we can call nuisance or dissimilarity, which needs to be combined with the coherent information to then give the image. So you have a way of explaining your data by means of coherent versus nuisance, and then a model that would couple those. And we don't know that model. There's not a formula that will give it to you. It's not convolution. It's just an unknown operation here. And of course, the neural network will realize this operation. So we'd like to get to a point where we can ask a neural network to build these explanation variables for whatever the data set is, the content of information, and summarize for me the writing style of any given person. And so if you can do that, and it is possible to do that nowadays, you can then perform a redataming task. So let's take a look at this busy slide here. What you're looking at with the black arrows is in fact what was used during training. It's at the top row here, you have a number of people, 3 here, but in reality it's maybe 100, who wrote the digit 6. And then in addition to that, the bottom row here, you have another set of 100 people who wrote the digit 9. If you have a proper representation of this data set with the proper rows of explanation of different variables, you ought to be able to fill in the missing images and give a prediction for how the top 100 people would have written the digit 9, for instance. Those are the dashed red arrows. Or how the bottom 100 people would have written the digit 6 against the dashed red arrows. If you have the proper representation that couples content with style. And what you're looking at here are indeed predictions that were made using the proper kind of neural network architecture, based on these concepts here. So it works really, really well when you know how to set it up. And so this kind of idea is, in fact, I claim, going to play an important role going forward in scientific prediction, where we don't necessarily have the usual tools such as partial differential equations. And I want to show you one of those in the context of a form of remote sensing here, which is seismic inversion, but that applies more broadly in remote sensing scenarios, where you have the idea that you want to infer a map of the subsurface from scattered waves, from waves that travel through the domain, reflect off of the heterogeneities, and you then record the echoes, and you'd like to be able to determine the structure that gave rise to these reflected waves. So that's seismic imaging, of course, which you can perform at different scales, but that's also ultrasound and radar, for instance. The mathematics of this is that you have a partial differential equation that will explain your waves as a function of the medium in which they travel, and the direct problem is then to determine the solution of this partial differential equation, meaning the wave field. And so I don't know if I necessarily want to go over the math of this, but take a look here at the image on the top right. That would be a situation of interest in geophysics, for instance. That would be a 2D Earth. That's the medium in which the waves propagate. And you have here a m of x is 1 over c squared, where c is the wave speed. So that is the fixed physical parameters that will enter your partial differential equation. In fact, if you look at the PDE, this is where they enter. It's the m of x here, and then you have the Laplacian, you have the frequency, the wave field is here, u, and f is going to be the source. It's going to be your earthquake or your antenna in the case of radar. And that is a very simple model for it, by no means the best at all in any given situation, but that gives you an idea of what's going on, the acoustic wave equation here. And running the forward model means given m, given f, find the solution u of this equation and record it at receivers. And if your receiver is here at the top of the domain, then you would have the typical situation in seismology where you have a bunch of seismograms. You are looking at here the bottom figure. The axes are going to be spaced from left to right. That's the x-axis. That's the receiver location. And then time increases pointing down. And so if you take a look at any given column of the image here, you follow a column and you look at whatever that function is, it's going to give you a typical seismogram. You start with 0, the wave hasn't arrived yet, and then some wiggles, the first wave arrives, you wait a little bit, some more wiggles for the second wave that arrives, and so forth. And so in seismology, you have these seismograms, you have an enormous number of them as a function of, so you have time, you have receiver location, you have source location, so you have high dimensional data sets of these seismograms. And it's a very important task of scientific prediction to be able to infer the medium that gave rise to these data. And so in particular here, the inverse problem will be, given a whole bunch of these images here in the bottom right, try to find the medium at the top that gave rise to it. And I think it's fair to say at this point that in spite of decades of research in trying to solve this problem called full waveform inversion, we're nowhere near able to solve this in a satisfactory manner. We can produce images, we can do things, but there's no guarantee that what you'll get is correct. You have non-convex optimization problems, you have incomplete data, and so forth. So an extremely relevant question that can be written fairly neatly as an optimization problem involving partial differential equations. Not much progress has been happening for quite a while in this area here, but it's a wonderful test bed for some of the new ideas that we have here now for machine learning. If there are any questions on the setup of what we mean by scientific prediction and what seismic inversion is in that context, I'm happy to take any questions now if anybody wants to interrupt me. We can always come back to this. All right, then I claim that the situation we've just talked about of solving the wave equation in a medium to be determined is in fact a little bit like the computer vision situation we had before. And the type of data sets you have in this context have explanatory components that are not at all unlike what we saw before with the handwritten digits. And in fact, dozens of examples like this. And so here, what I mean by that is that whatever the data set here is on the left, you're going to have different instances of these seismograms that correspond to different sources, different earthquakes, but they all propagate in the same earth. So that means that you have an explanation of those data that consists in saying there's a coherent component that's the same for everybody, that's the earth in which the waves propagated, and that there's going to be dissimilar components that give you different instances that correspond to the different sources, the different earthquakes, which plays the role of the different style that we had for in the handwritten digits example. The Earth's model is a super high dimensional, but corresponds to the idea of what is the coherent information that used to be the digit 0 to 9. Now we're talking about a map of a parameter as a function of x, y, z. But morally speaking, it's the same situation as we saw before: coherent components and dissimilar components in the explanation. There is, in fact, a well-known way to go to combine the physical information of the Earth with the sources of earthquakes of location and types of fault lines and so forth. That's the partial differential equation. But in general, I'm going to assume that it's unknown as well. We're not going to put that in the neural network representation, and it is definitely not the convolutional model, even if you know the PDE, because you don't know where the source is and what its mechanism is. Okay, so that's really interesting for us because we're gonna say, let's write down a neural network that will reproduce the data, but is not the partial differential equation. But however, it inherits some features of it in the sense that there's coherent information and there's dissimilar information. And the kind of game we can now play is going to be a little similar to the game we played in the case of handwritten digits. We might be able to generate data that was never seen, to generate virtual data without ever looking at the partial differential equation. That was the case for handwritten digits from somebody who had only written, let's say, 0 to 4, and I want to generate 5 through 9. You're in a similar situation here. If you've only observed the solution of your equation in restricted setting, you might be able to generate virtual data that was never seen. Take the following example. Imagine here that you have the x-axis and the y-axis called G and W here. G is going to be for Green's function, and W is a typical letter we use for signature of a wave. So wave versus Green's function. The x-axis here is my coherent component. It's going to be how the Earth might change very slowly over time. And so here I have in mind applications such as carbon injection, for instance, or mining of hydrogen, where you are going to have very slow changes of the Earth. And one of the major engineering challenges nowadays in this geophysics situation will be to monitor whatever happens using remote sensing, and here in this particular case, seismic waves. And the kinds of data that you have are very indirect images of the subsurface. And so you're going to have here recordings of waves that scattered off of the Earth, the baseline Earth on year 1, where you have a bunch of earthquakes or maybe even incoherent recordings based on seismic noise, passive recordings of waves. You do not control at all whatever those sources are, but you record those waves. And you know they correspond to the Earth on year 1. Fast forward, wait 5 years, whatever those activities are, they've changed the Earth a little bit. You want to monitor what happens. You now have access to new sources of waves that are not at all the same as before. You're not going to have the luxury of having the same earthquakes. You don't have the same seismic noise for passive recordings. You have new recordings here. You have a bunch of them because you can do that over several days, for instance. So you have several events correspond to waves coming from different directions or different point sources or different plane waves from infinity, things like that. But they're not at all the same. And so our goal here is to say, even though we don't know the PDE, we certainly don't know the medium to plug into the PDE, we'd like to be able to generate the virtual data that would correspond to whatever the response of the Earth on year 1 would have been if we used the sources that gave rise to data on year 5. Or conversely, what would the data have been if we had used the source here that were sent waves in the Earth on year 1, but for the response of the Earth on year 5. And so we don't see those virtual data, but we would really like to be able to have them. And my claim is that neural networks are an amazing way to do that, to do this sort of, redataming, sort of fancy signal processing, but not at all classical. We don't have methods that would do that in general in the classical case. And what's the point? If you can do such a thing, and you can do this form of redataming here, look at what you have here on the top line. If you can take the difference of the virtual and the recorded data set for those sources here, you have a comparison between what we call the baseline and the monitor Earth. Take the difference of those two data sets now. Whatever will pop out corresponds to whatever happened in the subsurface that's different between these two scenarios, and not all the rest, the complexity of what we call the overburden. So for imaging now, if you apply a regular imaging algorithm like back projection, migration, what have you, that is standard to the difference of those two images now you have an amazing way of being able to image the subsurface for what we call time-lapse or 4D seismic monitoring. So there are important implications of the ability to do this. But my message to you today is that, yeah, neural networks, if properly done, will give you the ability to create these virtual data. And I want to convince you now that, maybe show you how, but also convince you that you might even get to the point where you can make a statement that this is actually trustworthy. You can trust this type of redataming from a neural network. It might actually be accurate. And in particular here, if you zoom onto these data sets to take a look at what they are, Pawan in my group is a geophysicist and is going to create these images and tell you, oh yes, they mean something to me geophysically. In particular, if you take a look at the virtual data that you generate here in the middle, borrowing the Earth from whatever this left situation here that was measured is, and the source from this right situation here, which was measured, is going to tell you, yes, those actually carry features of the waves on the right here. We see the frequency content is close to this image here in this portion, but then whatever the amplitude here in this portion here is borrowed from this image and not so much from that image here. So it's a very fancy way of interpolating between the two in the correct space. And I'm not showing you the validation for this example here because it is visually indistinguishable from the prediction of the neural network. We have a couple of percent of accuracy level here, so visually it is indistinguishable. It works amazingly well. So why would it be that you're able to, let's go, turn back to mathematics now. Why would it be that we should be able to make these kinds of predictions about systems for which we know very little? This is not based on a partial differential equation. It's based on the neural network, and there's a redataming question. So there's an underlying model for both situations that we've seen, both examples, that's of the form, large matrix Xij, in fact, a block matrix within this is Xij, generated by some predictor with a generative AI and then BJ. Think of the case of a rank 1 matrix as a very special example of this, where you have a large matrix that's generated from just the product of AI times BJ. In general, you have much more general functions F here, but of limited complexity that will expand, the reach of the product, and you have something that's more general now. And so this is no longer rank 1 matrix recovery. The redataming would be the idea that you observe partial entries of this matrix AI Xij here, and you'd like to recover those that are missing. This is what we mean by redataming. We'd like to know it's accurate. Of course, in the context of matrix completion or matrix recovery, we've seen people, produce really outstanding results, from the mathematics community for low-rank matrix completion, for instance. What we have here is a vast generalization of that we can call latent rank 1. And I want to convince you that this is everywhere in nature around us. This idea that nature is somehow latent low rank is something that, invites the definition of low complexity classes of functions and data. Imagine a third example that I don't have on the slide is you have to look at me or imagine what I'm telling you. Imagine that you have here the room I'm in, and you're going to see a bunch of pictures different from different angles of the room that I am in, let's say. And I'm asking you to characterize the complexity of the set of these pictures that you have. And I claim it's not going to be the number of pixels on the image times the number of images, that's n1 times n2. I'm claiming the overall complexity of the data set is not n1 times n2, but it's really more something like n1 plus n2, where n1 is going to be the complexity of specifying the 3D scene, and n2 is a number of different locations where I might place the camera. It's not an n1 times n2 situation, it's an n1 plus n2 situation. And the same thing is true for low rank matrices. If you have vectors a vector in Rn1 for A and a vector in Rn2 for B, then the complexity of the rank 1 matrix formed from the outer product of A and B is not going to be n1 times n2. It's really n1 plus n2. And so that's something to keep in mind. Nature is like that. When you have the idea that you have an object and you have sensing, then it's the complexity of the object plus the complexity of the sensing. That's the intrinsic complexity level of your data set. It's not n1 times n2. We don't have access to the map F that creates that. Nature gives us the X. It doesn't give us the explanation F. Or maybe some people think they do when they have partial differential equations, but we're not going to worry about that. The network's explanation, what we'd like to be able to do is build a neural network that replicates this structure of having the explanation variables A and B that enter in this form here. We're not going to be able to get them exactly. If you give you the example of images of a room, for instance, I'm not going to be able with a neural network to be able to infer exactly the 3D scene of the room and where the pictures were taken from. But nevertheless, if you auto-encode this data set in the proper way, you might be able to get an explanation using new variables Z that replace A and Z that replace B. That would be called latent variables, for instance. And G would then become a generator. That would be generative AI. And so then it becomes now a matrix recovery question. If you know there's the kind of complexity class you're dealing with here, and you observe certain entries of the matrix Aij, can you claim that you can recover the missing entries accurately? So it becomes a mathematical question now, given this very generalized low rank model for the data. And I'm also including the word here, symmetry. And this was in the title of my talk also. We're talking about symmetry under permutations. And in particular here, something like that happens when you have a model like this, or even in the low rank case. If you go ahead and you permute the entries along the row index I, it's not going to change your job of determining the other vector, the bj. If you permute the i's here, it's not going to change your task of determining the bj. And conversely, if you permute the j, it's not going change your task of determining the AI. Meaning, if you feed the data in a different order, if you permute the I's, it's not going to change the B's and vice versa. So there's a symmetry under permutations that's happening here. That's actually a way of expressing this equation differently. So how does it work? How could we ever get to the point where we can make predictions and find missing entries in the matrix Xij such as this, or finding the red images here when we only observe the black ones? And the idea is, yes, there's a way to do this. I don't know how much time I want to spend on this, but it's the idea that you want to have, it's a very busy slide, you want to have an autoencoder representation of the data that would be in the X matrix that you just saw, that is in a way not the usual autoencoder, which would be like some form of PCA, but in fact invites us to define variables with roles in the middle of autoencoding. So let's take a look one step at a time to this picture here. On the left, you have a data set that you'd like to be able to reproduce with the neural network. So on the right here, you have the reproduce instances, and the loss function of this autoencoder, if you're not familiar here, will just be the expectation of the difference between those properly discretized. So you just want to reproduce in a least square sense all these images. Then the idea of autoencoder is that you have a bottleneck of information in the middle. So the big picture kind of approach to this complicated picture here would be to say, on the left, whatever is surrounded by my mouse pointer here is some form of encoder. It's like, dot products with the right singular vectors, for instance. Whatever's in the middle is what we call latent variables. It's much reduced dimensionality compared to the input space here. And then whatever happens on the right here would be the decoder. So in the context of PCA, they have the singular values, and they have the left singular vectors here that would appear, for instance. And the decoder. So autoencoders are at heart this architecture of having an encoder, latent variables, decoder to reproduce a data set. This is unsupervised learning. We just have points in high dimensions that we want to reproduce. Fine, but this is not going to achieve the goal that we want, to be able to understand and disentangle the explanations. If, however, now you say, give me different roles from a different latent variables, like give them meaning, control what they really mean, you might be able to do a lot of really interesting things with prediction. In particular here, look at what happens in this box here that I call symmetric autoencoder. What I'm asking here is that when you feed those instances together into this encoder, I want the result of encoding to be independent of the permutation of those instances. If I feed those instances in a different order, I want the result to be permutation independent. Why? Because here, for instance, I want this to contain the information of the digit 3 that doesn't depend on the order in which these images appear in the training. So I'd like to have an encoder that specifically behaves in a way that's independent with respect to those permutations, and you can do that by a general encoder summing over the instance index and then having another encoder here. There are other ways of doing it. This is the simplest. You could also do sorting. Those would also be permutation independent. There are different things you can do. And then whatever the rest of the picture here is for the encoder, I don't necessarily want to go over the details of this, but it's the rest. Whatever the encoder needs to be to encode the rest, meaning the style here, what we call the nuisance parameters, is going to be the second branch of my autoencoder, is whatever happens here in the bottom. The idea is that you should encourage information to flow to the symmetric branch instead of the general branch here at the bottom. There are tricks for doing that. This is what we call dropouts here, for instance. But what matters is that we have another code here, latent code, that carries the style or the nuisance, which allow us to say those instances are different from one another and how they're different from one another. Then the decoder is whatever is needed to put those codes back together and form the data set. So that is what we call symmetric autoencoder. And these are ideas that have been around, in different communities. And we're just trying to deploy this here in the context of scientific prediction. And this is what works remarkably well. This is what gives you prediction of the digits that you saw earlier. This is what gave you the seismic redataming that you saw earlier. It works amazingly well when it's properly trained. There's still a lot of work to make this work, but that's the idea. So mathematically then, what kind of result can we expect to have? Can we actually make a claim that whatever redataming here would be accurate? First of all, what is redataming? How can we generate virtual data that were never seen given an architecture like this? Look at what you can do. This is almost like gene splicing. You will start from the data, encode it using this architecture to give you the latent codes that are here, the boxes in the middle. Keep those, save those, and then if I ask you to then have the digit 9 from user X, I would borrow the coherent code for the digit 9. I would borrow the style code for person X, put those together. They were never seen together during training, but now I have them. I put them together. I run through those through the decoder, and we have the output being the redataming. The redataming meaning the virtual data. It's just by borrowing the codes, because we know what they mean, we borrow them, we mix and match, we swap the codes, and we can create data this way. So you could create those fake seismic data, for instance. The deep fakes for video, sound can be done this way. The idea of doing, what would a picture look like if we had been looking at the scene from a different angle, for instance, would have been a similar game of mix and matching codes here and then sending them into a generator. The decoder is generative AI, is a generator. So mathematically, how can we expect that this idea of generating virtual data by swapping codes could ever be accurate? And the answer is, well, surprisingly, we might be able to explain that in some context, for which now we do math, so it's going to have assumptions to our theorems. So imagine that we want to find a matrix X from observations given by a linear map, script A here. And so we're going to call Y equals script A of X. The standard setting for inverse problems. Now, in our case, X is going to be a matrix, A is going to pick entries in it, and Y is going to be the observations of those entries in the matrix. That would be the situation of interest here. But you can imagine compressed sensing fits in this framework also. So the new thing is that we require that this capital X, sorry, not smart, this capital X is in the range of a generator for some deep generator that gets trained alongside the determination of the latent variables. So you know that your X needs to be of the form script G of Z. So going back to my previous slide here, those codes in the middle, that's going to be Z, and the decoder here is going to be script G, that's the generator. And we need to determine both from the training set. So the maximum likelihood estimator here for Z and G, both of them, not just Z for fixed G, but both of them at the same time, is for Z of the proper dimension and for G in a proper class of generative networks, minimize the least squares misfit. How could this ever work? You have an enormous number of parameters in both in Z and G. Well, okay, but you also have lots of measurements. So the complexity of Z and G might be adequately limited. In particular, the Z is low dimensional. Remember the story I made, the big deal I made about how the overall complexity level of a data set is not N1 times N2, but is N1 plus N2. The complexity of the coherent component plus the complexity of the sensing and the styling that goes with it. It's not the product of the two, even though the data set is in Rn1 times N2, the intrinsic level of complexity is N1 plus N2. That's going to be the length of the latent code. And then the network itself, you have to find a way to characterize the complexity class of your neural network. And this is where different networks will give rise to different results. But you can certainly say if you have a dense ReLU network with ReLU activation functions, rectify linear units, width W for the network, depth D. And so you are going to have, that's going to be limit the complexity of what you can train. So for us, again, the situation is that of some form of matrix completion, where we observe certain blocks in the matrix here. In other words, going back here, we observe some of those images here, those black ones correspond to some couples ij in this matrix capital X. X naught means that the original one we don't know, we'd like to recover, that carries everybody, carries all these images here. So it's a very, very large matrix here. And the measurements then are going to be some of those blocks. So those ij blocks for ij in some set omega. So that the measurements are going to be the script A applied to this X naught. And here script A is just going to be the binary mask onto the blocks that we see. That's going to be the measurements. And then Y is the concatenation of all these blocks that we observe. I would love to be able to write a theorem with A being those measurements given by blocks of a matrix, entries sampled of a matrix, or even random models for it. I cannot do that, so today I cannot show you a theorem with this kind of model. However, what we're going to do is idealize those measurements by saying that A are just inner products with Gaussian IID random matrices, and the number of measurements that we have here is going to be M. So very standard thing to do in compressed sensing. We start with the simplest measurements you can possibly get, which are random, try to understand that probabilistically, then walk back to see what other measurements we can do with later. But for now, this is what we're going to assume. Y equals A of X naught. X naught is a matrix of this form here. We observe some limited amount of information about it. M rows of such a random matrix. We'd like to be able to determine the matrix X naught. So the standard matrix recovery problem. We've completed our trek almost all the way from this original these applications and from inverse problems, almost all the way to matrix recovery and compressed sensing, so that we can do math about it. And so then you have the following result. We want to know if we have recovery. Recovery means the following thing. It means among all the possible objects that are in the range of my generator that can be generated by my decoder, if your training error is adequately small, and in this case we idealize it as being 0, which is not a big restriction. We might be able to walk that back. But if the training error is 0, and we can have that the measurements match for the original object of interest, and the one we recover from autoencoding, the question is, do we have X equals X naught, meaning we match the original object and we can claim that our prediction is accurate and here is exact. The complexity of the latent variables, again, is that they are in a low dimensional Rn. They are in R bigger of N1 plus N2. And the complexity of the generator is going to be, morally speaking, the Lipschitz constant of it. And we can mathematically use sigma be the product of all squared spectral norms of weights of the decoder, and it's a quantity that's independent of N1 and N2, the dimension of the latent variables that feed into this network, because of an effect of large sample sizes is convergence there, so we can have that this sigma is independent of N1 and 2. So this sigma is related to Lipschitz constant of G and is related to the W and the D that you saw before for the width and the depth. Morally speaking, I think this sigma is on the order of W to a power that's on the order of D. That's what the Lipschitz constant will end up being. And the theorem goes as follows. If the setup is what we saw before with random IID measurements of this matrix capital X that comes from the range of a generator, and if the number of measurements, meaning the number of rows of this random matrix, is greater than N1 plus N2 with a constant that's sigma squared and then another numerical constant and logarithmic terms that I'm not writing down. So if you operate at the information level of the object you're trying to recover, meaning both the latent variables and the neural network, then you have enough information, meaning enough training samples. The sample complexity is high enough that you're going to have you have perfect recovery with high probability, X equals X naught, provided the measurements match, meaning the training here is done without error, A of X naught equals A of X. So you see, it's in the fashion of a theorem like matrix completion or compressed sensing, where you say if the number of measurements is high enough, the number the data match up to an error level here, which is 0, then you can recover the object of interest in the complexity class that you started from, like k-sparse or rank k, for instance. Here, something very similar happens where the notion of number of measurements, becomes sample size, and the notion of low misfit becomes the idea of low training error. The idea of regularization by L1 or nuclear norm becomes the idea you're in the range of some generator. But the type of results that we can come up with, have done a similar flavor with high probability. High probability here means 1 minus exponential in decaying exponential in m, the number of measurements, as is standard in compressed sensing, then x equals x naught. So you actually have in this setting, which has its own assumptions, but you have an instance of a theorem where you can claim that the output of a neural network is going to be exactly what you want it to be, which is a bit unusual. And so just for the specialists, because I'm going to stop here, but just for the specialists who know this already, for those of you who don't, it doesn't matter. But the type of techniques that you're looking at to prove such results come from a high probability and are going to be familiar to you if you work in this area of let's say, math of information and recovery theory. In particular, you have this idea of restricted isometry property that now gets generalized to smallest singular values on the subset. You're going to have Gaussian width coordinate escape to the mesh lemma. You're going to have metric entropies of the range of the generator that comes from covering numbers. So yeah, the Gaussian width is related to the covering number of the range of G, things like that. So it's a nice way to couple some of these techniques that are by now well developed in let's say compressed sensing, matrix completion, and a recovery theory, and apply that to situations where now we're talking about a range of deep generators. So this is my last slide. I wanted to show you, I hope I managed to show you that it is possible to talk about important questions of scientific machine learning with new tools that go way beyond classical inverse problem, optimization methods, where we respect the fact that the data might not match a PD exactly, but where we might be able to make prediction tasks with resemblance to the PD. Those neural networks that we deploy don't have a PD with specific parameters in it, but the latent variables that it has in it play the role of those parameters in those partial differential equations, and obey certain kind of leftover remnants, such as invariance under permutations, for instance, which was present in the PD and is present in the DeepNet here, for instance. So it's pretty amazing what's happening here. I think it makes an enormous difference. We cannot ignore this anymore. So it's important for our community to embrace these ideas and try to make sense of them. It's very complicated, obviously. This is only the beginning. This is one simple example where things work, but I want to stress that there are also things that do not work necessarily or very difficult. And we are giving up a few things when we switch to deep nets instead of traditional, let's say, imaging methods. Interpretability is one of them. Guarantees is another one. We're trying to make inroads, but the question is wide open. And we also don't know if we are actually doing science anymore. We have, this is engineering. We're not doing the scientific method here. This is not Occam's razor. This is not try to find me the simplest explanation. This is not testing a hypothesis. This is just a brute force engineering way of making a prediction, and it might not be reliable at all. So let's not lose sight of the fact that we're walking away from science sometimes when we deploy these predictors, and it would be a good idea to make sure that we connect back to science. And I think this is where some of the research should be going forward. So that's it for me. Thank you very much.
Okay, so